All right, guys, Unit 3, Lesson 7, we're looking at determining average and instantaneous rate of change for rational functions. We've already looked at rate of change in Unit 1, and we looked at calculating the average and instantaneous rate of change of polynomial functions, and now we are expanding that to calculate the rate of change of rational functions. So our formulas still stay the exact same. So when we're looking at average rate of change, we're looking at determining on average at what rate is a function changing between 2 points or on an interval. Okay, so between 2 points slash on an interval. So if we had some, let's say, like a quadratic function that looked like this, that's not that nice looking. Let's just say it looks like this. We could be interested in, what's happening between here and here. So we said, okay, well, here it's got this function value, and over here it's got this function value, and on average, we call this the secant line. Technically, it should go right through the curve there. But on average, what is the rate that the function is changing on that interval? So we would draw this like kind of the secant line, and then what we're doing is we're calculating the slope of that line using our formula that you guys have been using since grade 9, right? So we've got our change in our change in y over change in x. This is the same as your y2 minus y1 over x2 minus x1, which is your delta y over delta x. Like we haven't changed anything. The bottom is still the same. What did your x value change by between here and here? And what did the function value change by? So you went from a function value of this up to a function value of this. So what did your function value change by? And what did your x value change by? And we determined that by subbing in the x values of interest into our formula. And then this is our formula for estimating, and we are always estimating in this class because we haven't learned the methods that you would learn in a calculus course to actually calculate the instantaneous rate of change. But when we're talking about estimating the instantaneous rate of change, instead of between 2 points, we are trying to estimate at exactly 1 point. So at a specific point. So if it was this same curve here and we were saying, well, what do you estimate the rate of change to be when x is -2, for example? So we want to know what is the rate of change at that exact point. And to calculate the rate of change, to estimate the instantaneous rate of change, we use something called the tangent line. And that's where we draw a line as best as we can that is going to just touch the curve at that 1 point and nowhere else. And it's going to, in theory, represent the rate of change at that exact point. And so this formula here is, the notation's a little different than we introduced in Unit 1, but basically we are using a centered approach in this course, and we can't just figure out, well, what's happening at x equals, let's say, -2. If there are point of interest, we want to know what is happening at x equals -2. We have to investigate by choosing an interval that is just before and just after. So we might say, okay, well, what about -2.01 is to the left, and what about -1.99 is to the right of that point? And what if we use these 2 points? Essentially, what we're doing is we're finding the average rate of change. We're using the exact same formula, but we're choosing 2 points that are so close to our point of interest. So we are hoping that the average between these 2 points comes really close to telling us the instantaneous rate of change at this point. And so the formula maybe looks scary, but really all you're doing is you're choosing some x value. In this case, it's -2, and you're taking away some consistent amount and you're adding that same amount. So you're making sure that your point of interest remains in the center of the interval. Okay, so there's a little bit of review for average and instantaneous rate of change. What is the difference between the two? How do we calculate them? So determine the average rate of change for the following function on the interval 1.5 to 3. So don't ever forget our vertical asymptotes. This function has a vertical asymptote at x equals 1. So it would not make sense for me to choose an interval of, for example, 0 to 2, Because what we know about asymptotes, we have a vertical asymptote at x equals 1. There could be some very different things happening on either side of that asymptote. So the average on that interval, 0 to 2, is really not telling me anything specific at all, because on one side it might be a positive rate of change, and on the other side it might be a negative rate of change, and it's over an asymptote. So we never want to investigate average rate of change over an asymptote. And because we have a vertical asymptote at x equals 1, we are going to look at what's happening to the right of that asymptote. So we're going to sub these values in here, and 1.5 is 3 over 2. So we're going to be looking at the interval 3 over 2 and 3. And you could just put these values in your calculator, but really what we're trying to sub in here is we say, okay, what is the function value at 3? And what is the function value at 1.5, which is 3 over 2? And what is that function value changing by? And then you're doing, and what did my x value change by between 3 and 3 over 2, or 1.5. So off to the side, maybe we're going to sub in our function value of 3. So when we sub in a function value of 3, we end up with 3 squared divided by 3 minus 1, which is 9 over 2. So I should just move these over a little and make sure we know what we're actually solving. So this is the average rate of change, and over the interval, we could write the interval here, but 3 over 2 to 3, and this is what we're calculating. So here we've got the function value at 3 is 9 over 2 minus the function value at 3 over 2. So this one's going to be a little funkier. We're going to have 3 over 2 squared divided by, I'm going to write it as division rather than as a quotient, because a quotient on top of a quotient is not that cool, divided by 3 halves. So remember that 3 over 2 is 1.5. So if I have 1.5 minus 1, I'm left with 0.5, which is 1 over 2. So I'm dividing that by 1 over 2. When you have an exponent being applied to a quotient, you have to apply it top and bottom. So this becomes 3 squared over 4 squared, which is 9 over 4. When you divide by a fraction, you keep the first fraction, you change your sign to multiplication, you flip the second fraction. So this becomes 9 times 2, which is 18 over 4. And I could divide top and bottom by 2 and get 9 over 2. Isn't that interesting? Okay, so now when we do that, we get 9 over 2 divided by 9 over 2. And on the bottom we have 3 minus a half, which is, we're left with a half, which is also 3 over 2. But we really don't have to go any further here, because what we can see is that 9 over 2 minus 9 over 2 is just 0. So we end up with 0 divided by 3 over 2, or 1.5, and that is just 0. So I actually didn't plan this, but this is kind of neat, and we can explain why this happens. So therefore, the average rate of change on the interval 1.5, or 3 over 2 to 3 is 0. Okay, so this isn't great, because a rate of change of 0 means it's not moving. The reason this happens is that this is a rational function where the degree of the numerator is greater than the degree of the denominator. So this would have a slant asymptote, and we would find the location of that by dividing this factor out from here, and the result would be some sort of slanted asymptote. Let's say, I'm just going to make it up, but it looks something like that. So on the right hand side of this vertical asymptote, which is where this interval is, the function is actually going from decreasing to increasing. And the reason that, and so when we look at the average over such a large interval from 1.5 all the way up to 3, at some points on that interval it's going down, and other parts it's going up, and it happens that I chose a interval where the turning point would be centered right in the middle, and the result is an average rate of change of 0, which is kind of neat because then it tells us that in the middle of this interval our function has a turning point. So that's kind of cool too. And we could double check this if we go over to Desmos and we said, okay, well, there's my function, f at x is equal to x squared over x minus 1. And remember, you can use Desmos. You can say, okay, I want to figure out what is f at 3 minus f at 3 over 2. And there we get that 0. And technically, we've not finished our calculation yet for rate of change. We would then divide all of this by 3 minus 3 over 2, and we still get that rate of change of 0. And again, this is why, because we have that turning point happening right on the right in the middle, and the result is an average rate of change of nothing. Okay, so not not the best example, but also kind of good to show you that we could get an average rate of change of 0, and also to show you why an average rate of change is not nearly as accurate as narrowing in on a very specific point. Because if we had said estimate the instantaneous rate of change at 3 or at 1.5, we would have got a very different answer. All right, so function, we're looking at a slightly different function, and that's what we're going to do. We're going to estimate the instantaneous rate of change for the following function at these 2 points, x equals -5 and at x equals -3. So again, the first thing we want to do is consider the location of any vertical asymptotes. So we are going to have a vertical asymptote at x equals -3. Well, that's interesting because that's one of the points we were going to estimate the instantaneous rate of change. So if we have a vertical asymptote happening at x equals -3, the function is not doing anything at exactly that point, right? We're estimating instantaneous. So right away, we could say vertical asymptote at x equals -3. Therefore, there is no rate of change at x equals -3. So that would be done, and that's going to save you a lot of time, because if you go subbing in -3.01 and -2.99 and all this stuff, it's just a waste of your time. There is no rate of change at x equals 3, or sorry, x equals -3. But what we can do is estimate the instantaneous rate of change at x equals -5. So if the point of interest, we'll call it, that we are interested is x equals -5, we have to choose a point that comes just before and just after or on either side. So -5, if that's over here somewhere, something that's a little bit further than that would be -5.01, and something that's not quite at -5 yet would be -4.99. So those are the x values that we're going to use, that are going to create an interval that is so close to our point of interest. But ultimately, our method is the exact same as our average rate of change. So we're saying, okay, well, what is happening at -5.01? And what is happening, and when I say what is happening, I mean what is the function value at -4.99? And what is the difference in those x values? And this is all to help us calculate the instantaneous rate of change. And it is approximately equal to this calculation. So I'm going to save us some time and just use Desmos for this. So our function is x divided by x plus 3, and I've already put this into Desmos. So we've got x divided by x plus 3. So we get rid of that one. And now we're dealing with g at x. So let's use that notation. So we want to know what is happening at -5.01. That is not what we're looking for. G at -5.01 minus what is happening, or what is the function value at -4.99, so on either side, divided by the change in x, -5.01 minus -4.99. And don't forget the denominator, because look what just happened there. If I get rid of those, it showed a negative rate of change, but when I divide by the change in x, it is also negative, and negative divided by negative is a positive. So not only do we have a positive rate of change, which is obviously different than a negative, we also know at what rate. So we have a rate of change of 0.75, positive 0.75. So positive 0.75. So therefore, the estimated instantaneous rate of change at x equals -5 is 0.75. And for this function here, we know that it has that vertical asymptote at -3. It's a linear over linear, so we take the leading coefficients, the quotient, to find the horizontal. So this is going to have a horizontal asymptote at x equals 1, sorry, y equals 1, not x. Getting carried away here. At y equals 1. So somewhere around here, we're going to have this horizontal asymptote, and this is -3. At -5, the function has a positive rate of change, so that should tell us that it has to be above this horizontal asymptote, because it needs to be increasing ever so slightly. It doesn't have a steep rate of change, not like here. We're looking at way over here, but it is going up, 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 despite my curve looking like it's going down. But it is a constant increase on the left-hand side of that asymptote. Now, if we had have got a negative rate of change at -5, that would have told us that the function is going down on or at that specific point. Okay, and we did not get a negative, so let's get that out of there. All right, so another example, so here we're looking at average rate of change from an equation on an interval. Then we're looking at instantaneous rate of change at a specific point, again, from the equation. And now we're looking at instantaneous rate of change from the graph. So here we have this function, this rational function that is graphed, and the question is saying to use the graph of the tangent line to estimate the instantaneous rate of change of the following function at x equals -4. So x equals -4 is right here, and the function value at that point is right here. Now, that is a value of -1, a function value. That does not tell us anything about the rate of change at that point. Now, hopefully we can see that it's a negative rate of change. At that point, the function is decreasing. But how we do this from a graph is we draw a tangent line. So we have to draw some line, and we have to get it. This is tricky because you're going to have to play around, but we have to try and get it just, oh gosh, at that point, and not passing through the graph anywhere else. So we've got to try, I'm just going to get it on here, but like that is not it. I can even see the green above. So I'm just going to get the line on here so that I can play around with it and move it. Okay, so I might be getting closer. It might honestly be better if I get rid of this red dot so we can see just how close we are. And it might be better if I even get a smaller line. Okay, that's pretty good. That's getting us pretty close to that point that we're interested in. I think it could slightly be moved up, like the curve, and then back down. I don't know. It's pretty close. Okay, you guys are like, yeah, we get it, but this is important stuff to make it accurate. Okay, so if we are looking at the calculating the instantaneous rate of change by using the slope of a tangent line, we have to first draw the tangent line, and by definition, the tangent line can only touch the curve at one exact point, and it has to be at that point of interest. So once we've drawn what we believe to be an accurate tangent line, so we've drawn this line right here, or at that point, I don't know what happened there. Now we can calculate the slope of that line by choosing another point that is on that line. So let's scan, and I think this one is looking like a pretty good one here. So it looks like we are going down. Now it's two boxes, but I will just say pay close attention because this is 1, -1, and then this is -2. So we're actually, if we're talking rise over run, we're going down 1. And then again, our x-axis is changing by 2s, so we're going up 1, and up another 1. So we're going up 2. So we have a rise of 1, -1, and a run of 2. So it's looking like the estimated instantaneous rate of change is roughly equal to -1 over 2, which is -0.5. Now, I hope that you guys understand that from the graph, this is not as accurate as it could be if we had the equation. And I'm just going to actually show you the equation of this and the actual instantaneous rate of change at x is equal to, or the estimated instantaneous rate of change at x is equal to -4. So there's the function that is displayed here. F at x is equal to 3x plus 1 divided by x squared minus 5. And when I use my interval, so just a little bit past the -4, a little bit before -4, and then the difference, yada yada, I get -0.45. So -0.45 versus -0.5. So like it's close, it's pretty close, but it's not exact. But if I had to, at least I for sure know that it is a negative rate of change. I know that it's not a super steep rate of change, and so it's all important information. Okay, so that's how we can find or estimate instantaneous rate of change from a graph. And then the very last question is an application question. So how can we use our understanding of rate of change when we are given a word problem or an application problem? And in this case, we're going to use technology to help us. So the snowshoe hare population in a newly created conservation area can be predicted over time by the model. P at t is equal to 50 plus, you guys can read, where P represents the population in size and T represents the time in years since the conservation area opened, okay? At what rate will the population be growing at time 12 years? Now, because we are given the function and we are being asked at an exact point, okay? So at a specific point, we are going to then be calculating, therefore, we need to find the estimated instantaneous rate of change at t equals 12 years. So, again, for sake of time, I'm going to use my Desmos calculator just because it helps us. But ultimately what we need to do is choose something that comes just a little bit before and a little bit after. So we could choose 11.99 years and 12.01. And this method works because we have the function formula, so we can, or the function equation, so we can plug anything we want into it. So ultimately, when we set it up, we would be saying that the estimated instantaneous rate of change is equal to, roughly, and we would be looking at the population at, and it doesn't matter the order because it'll all come out in the wash, at 11.99 years minus the population at 12.01 years. What did the population change by over the time span, the difference between these two? Okay, and so again, absolutely, and on a test, you can sub 11.99 into here, right? We would do probably all of this first. So we would do 11.99 squared, then we would multiply that by 2,500, then we would divide, and in brackets, we would do 25 plus 11.99 squared. We'd get that amount, then we would add 50. And if we were doing this on a calculator, and if you want the practice, because some of us are really struggling with calculator work, absolutely do that. But do make sure that you keep all your decimal places because it does make a big difference, because these two values are going to be so close together. Like it's only like a difference of like a couple days in population, right? So then you would record that amount, then you would do it all over again. You'd sub in 12.01, and then you would find the difference between 11.99, 12.01. Then you'd be dividing by that 0.02. So we're going to use Desmos, and there's our function p at x. And so we want to know the population difference from 11.99 years to 12.01 years, and there's what the population has changed by. And again, notice how it's a negative, but when we do 11.99 minus 12.01, that's also a negative, so it makes it a positive. So 52.52, let's call it, is what we got for the estimated instantaneous rate of change at time equals 12. So 52 52.52, I think is what I said. Is that what I said? 52.52. Okay, and this is a word problem. So we're going to say, therefore, it is estimated that at exactly 12 years, the population of snowshoe hare is increasing. It's a positive rate of change, is increasing by 52.52, or we could just say by approximately 53 hairs. That might be because we're not going to go up by a half of a hair. So is increasing by approximately 53 hairs per year at year 12. Okay, so there's a bit of an application question for you where you're looking at rate of change. These calculations do take a long time. It's a lot of substitution. Some of us, like I said, are still really struggling with. Desmos is great for using substitution, but I do recommend you are competent with your calculator because you won't have necessarily access to an online or graphing calculator when you go to university next year. So I know it takes a long time, and this is like really important that you understand the approach. And so certainly you can use something like Desmos for, maybe most of the questions, but do at least a couple by hand to make sure you know how to use your calculator. And there's your practice. There's not a ton for rate of change of rational questions, but again, the questions are they're big calculations. So there's 3 questions for you, and then the exit ticket as well. Okay, have a good day, guys.